Mr. Rankin, giving you your lesson for today on radioactive decay. All right, disregard that code. You can use the code that I put on your Google Classroom page for the student paste. All right, today's teaching point: how can scientists collect quantitative data to date rock masses and fossils? Launch: what does the word radioactive describe about an element like carbon? All right, so looking at the two graphs, we have time along the x-axis, right? Time, rule of thumb, is always going to be your independent variable. And in this case, your dependent variable on the y-axis is what you're measuring. So we're measuring the decay product, how much is left over. Here, this is the decaying element, right? This is the decaying product. The product is the aftermath of a chemical reaction, or in this case, of radioactive decay, going from an unstable isotope to a stable isotope. All right, so radioactive, which would indicate something that is unstable, must become stable. And looking at these two graphs, we notice that at time 0, we have 100% of carbon-14 remaining, and we have 0% as the decay product of N14. This is what it decays into, right? Decay product. As time increases, we can see that the percentage of carbon-14 decreases with time, and here we can see that the N14 will increase in time. And this is not a linear graph. This is more of an exponential growth and an exponential decrease, or a negative, all right, just a decreasing value, all right, decreasing value, increasing value. Both of these have the same half-life, so you have 5.7, and this is all to the third, 10 to the third year, so really that's 5,700, and then 11,400, 17,100, 22,800, right? This is going to be half-life 1, half-life 2, half-life 3, half-life 4. All right, moving on, we have isotopes, atoms that contain different numbers of neutrons, but the same number of protons. Now, looking at this picture here, this carbon, which is carbon-12, is the one that you would see on the periodic table of elements. All right, and based on that, that should read as 6 protons on the periodic table of elements, and the atomic mass would be 12. And the way we get the atomic mass is from the nucleus. Now, the nucleus is at the center of the atom, and that would have the most mass. And the center of the atom consists of protons and neutrons. On the outside, these rings are like the electrons, or the electron cloud. That has low mass and really is not involved with the overall mass of the element or the atom. Carbon-13 now has one more neutron, right, which makes 6 and 7 a total of 13. So that's carbon-13. It's still carbon, 6 protons. Now the atomic mass is 1 more, making it heavier and unstable. This carbon-12 is the most stable, right? That's the stable element. Now it's becoming unstable, all right? And carbon-14, which you see on your reference table, carbon-14, right, it's still carbon, it's 6 protons in the nucleus. Now we have 2 additional neutrons from carbon-12, which will give you 8 and 6, will give you a total of 14. 14 for the mass. All right, so isotopes. There's so many isotopes out there. I mean, you probably name an element, I'm pretty sure that there's going to be at least 1 or 2 or 3 or 4 or 5 isotopes sometimes for one particular element. And carbon-13 wants to become stable. Carbon-14 also wants to become stable. Carbon-14 is not in abundance of, but carbon-14 is in basically every single living thing, including humans. We have carbon-14 in our makeup. Carbon is the building block of all living things. All right, if you look at your reference table on page 7, if you look at bituminous coal as an example, that's compacted plant remains, living things, that's made up of carbon. All right, let's check this out.
In today's video, we're going to look at the terms activity and half-life, and see how we can calculate each of them. We've already seen that some materials contain unstable isotopes, and that in order to become more stable, they can decay by emitting some form of radiation, like an alpha particle, a beta particle, or gamma rays. We call materials like this radioactive, and they come in loads of different forms. If we were to consider a single radioactive isotope, we'd have absolutely no way of knowing when it would decay, because the decay process is completely random. However, if we have a large enough sample of radioactive isotopes, then even though we couldn't tell when any individual isotope would decay, we can still find out 2 very useful things. One is the activity of the sample, which is the overall rate of decay of all the isotopes in our sample. And we measure activity in becquerels, where 1 becquerel represents 1 decay per second. So if a sample had an activity of 600 becquerels, then there must be 600 isotopes decaying each second in that sample. The other important term to know is half-life, which has 2 definitions, and can be defined either as the time taken for the number of radioactive nuclei in a sample to half, for example, to drop from 1,000,000 unstable nuclei to only 500,000, or the time taken for the number of decays, so the activity, to half. For example, to drop from 600 decays per second to 300 decays per second. To properly understand these concepts, let's imagine our radioactive sample as 100 unstable isotopes, each of which can decay by emitting radiation in order to become stable. So if we watch this sample decay, the first thing we notice is that the decay process is completely random. So we have no way of knowing when any particular particle will decay. As time goes on though, and more of them decay, the number of unstable particles remaining decreases. Because there are fewer particles left to decay, this means that the overall rate of decay, which remember is the activity, will also decrease. Which is why it looks like the sample is decaying more slowly than it was at the start. This is why we can define half-life as a halving of either the number of radioactive nuclei remaining, or a halving of the activity. They are both perfectly correlated, because fewer radioactive nuclei means a lower activity. Another way to show this decay process is by using a graph that plots activity in becquerels against time. As time goes on, the number of particles remaining and the activity of the sample will decline. But the rate of decline will also fall, which is...
I just want to let you guys know that becquerels would not be on any graph or anything you're working with. More than likely, you will have percent on the y-axis.
So in this case, drop from 600 to 300, which we can see is about 2 hours.
That's the first half-life.
And to confirm this, we could check another one by seeing how long it takes it to halve again down to 150. And indeed, it does take another 2 hours, so we can be confident that the half-life is 2 hours. If we had a different
Half-life
radioactive sample, though,
is
like
half
this one, we can see that it's decaying
of your
much
original
more quickly.
substance.
This means that it started with a much higher activity, as we can see on our graph, and also that it will decline much more rapidly, and so a much shorter half-life.
Half of 2,000 is
1
1,000. That was a quicker half-life. Okay. All right, so half-life, right? The time it takes for half of a sample of radioactive isotope to break down into stable isotope or into a stable isotope. According to this here, right, like I said, we're not going to have becquerels along the y-axis. You're going to usually have percents, all right? So percent remaining of carbon-14, which is your radioactive isotope, that's going to decrease with time, right? Notice that the line is decreasing in value. So the first half-life, right, half of 100% would be 50%, right? Bring this down, that's going to be half-life 1. And then you would have a means of measuring that with time. Since this is carbon-14, your reference table advises you that it is 5.7 times 10 to the 3 years. So the first half-life is roughly 5,700 years. That's how long it's going to take for half of the sample to decay into the stable product. Right, then half of 50 is 25, right? And then according to the graph, that would be your second half-life, right? That would be another 5,700 years, or another 5.7 times 10 to the third years, which will give you 11,400 years, or in scientific notation, 11.4 times 10 to the third power. Or you could do 114 times 10 to the second power. Or you could have done 1.14 times 10 to the fourth power. There's all different ways you can do that, all right? But I would kind of stick to numerical form in case if you are not that great with scientific notation. All right, half of 25 is 12.5. That will give you third half-life. And then magically, we have another half-life here. So half of 12.5 would be 6.25% remaining. Now, this is something pretty cool. After the first half-life, both the stable and unstable isotope are the same amount. So as this substance begins to decay, right? So if you have half, right? Let's say we had, so 50% of the original mass here has decayed. That means that 50%, the remaining 50% that's not there anymore is now in the new stable product. 50% decayed plus 50% for the decayed product will give you the 100% that you started off with. Right? Half-life 2, as an example now, you have 25% remaining as unstable, and you have 75% that has become stable, right? And 25 and 75 will give you 100%. All right, here they give you grams, right? So 10 grams was the original substance, right? If 5 grams is now still left over, that means that there's still 5 grams that decayed into the stable isotope. 2.5 grams is still remaining. That means that 7.5 grams has decayed. So at the first half-life, you will always have the same amount. Okay, absolute dating methods, right? So let's get this down, please. As time increases, the mass or percentage of the unstable isotope decreases, all right? So if you look at your graph, we see that time is on the x-axis and the mass of the unstable isotope in grams, or it could be in percent remaining, is along your y-axis, which is your dependent variable. So as time increases, because always work on the x-axis, as time increases, the mass of the unstable isotope decreases. Right? We learned this in lab number 4. This is considered an indirect relationship or an inverse relationship. All right, now this is the opposite, right? So now copy this down. As time increases, the mass or percentage of the stable isotope increases. If you want to draw these graphs, you certainly can. All right, so as time, you're going to put time here on the x, mass of the stable isotope in grams along the y. That can easily be percent remaining. As time increases, we can see that this line increases as well. And this would be considered a direct relationship from our lab on graphing in lab number 4. All right, so you have all of your half-lives that are here. 5.7 times 10 to the third is 5,700 years in numerical form. 1.3 times 10 to the 9, right? This is a positive power, so you have to move this decimal place over 9 spaces. This comes out to be 1,300,000,000 years. 4.5 times 10 to the 9th power. Again, that's a positive power here. You get to move this decimal place over 9 places. This would be 4,500,000,000 years. Last one is to the 10th power. That's 4.9 times 10 to the 10th. You're going to move this over 10 spaces, right? And this would be 49 billion years. All right, so these are the 4 that you need to know for this unit and for your exam. So carbon-14, right, is your unstable, N14 is your stable. Just a quick review. Potassium-40, K40, right, this is all the atomic masses, by the way. That can change into AR40. Now, AR is not on your reference table. AR is here, right? You can write this down, right? That's going to be argon. Then you have uranium-238, right, which is your unstable, and you have PB, that's in your reference table, and that's going to be for lead. Oh, forgot about the Ca. I'm sorry. So potassium can be 2 things. So Ar is argon. Ca, that's on your reference table. Ca is calcium, calcium-40. Last one is Rb, right? That gives you to you right here rubidium-87, but it doesn't give you what Sr is. Sr is called strontium, strontium-87. All right, they're not going to ask you to memorize these, but I just wanted to let you know what Ar and Sr mean. All right, another quick thing here is that when you're working with elements, just how we had in our first lesson together in September, unlike air masses, the first letter is always uppercase. Second letter is lowercase. Sometimes there's only one letter. If there's only one letter, that letter must be uppercase. All right, if you don't have it that way, you're not going to get credit for that on your big test in June. All right, here we go. Sample problem. A sample of wood originally contained 500 grams of carbon-14, 14C. I should really made this a superscript, right? Because usually the mass is located on top, but that's okay. Now contains only 31.25 grams. Approximately how many years ago was this sample part of a living tree? Step 1, create a 4-column chart. All right, so when you're creating a 4-column chart, we're talking about half-life. You could do this in any way you want, okay? I usually put half-life first, then you're going to put your unstable second, which is carbon-14. Notice how I made that the superscript on top. Almost like a power, but it's to the left of the element. Then I have your stable. Then I have time in years. All right, we're dealing with carbon-14. All right, so at time, you should probably do this on your own, but if you want to pause it, try this on your own. All right, if not, then just follow along with me. Right, this should be in your notebook. Right, so half-life 0, that's a great 0. The carbon-14, right, grams is 500 we start off with. So 0, 500. That's in grams. So I'm going to put in parentheses here 100%. That means that the N14 has 0 grams. Now I'm not going to put any units here because my unit's already up here in the title of that column. And that's going to be 0%. And that's going to be times 0. All right, let's move on. First half-life. We know that's going to be, let's do this in numerical form. All right, maybe I'll give you both. 5,700 years. And this is 5.7 times 10 to the third power. Right, half of 500 is 250. And that's 50%. And that means that the remaining 50% has decayed, which will be now decayed as 250 grams. All right, good way to check yourself is that after each half-life, you have to have a balance of what you started off with. We started off with 100%, 50 and 50 in half-life. 1 is 100, that adds up to 100%, right, because we have 0 here. And we started off with 500 grams. 250 in half-life 1 for the unstable, 250 for your stable. Add them together, that will give you 500. All right, let's continue. Half-life 2 would be 5,700 times up by 2.
Please excuse
Sorry, guys.
interruption. This is a reminder.
11,000.
The final teacher tenure cohort meeting of the year will be held at 7:30 a.m.
Okay, there you go.
in the first floor conference
All right, sorry for that.
Thank you.
All right, so 11,400. And scientific notation, that's going to be 11.4 times 10 to the third. Okay, it might be a little hard to see. All right, let me brighten up the screen here a little bit more. All right, now half, right, we have to do half of 250 right now. So if you take half of 250, right, that will give you 125, right? So we have 125. Half of 50 is 25%. Now we have to have a balance, right? So if 125 grams, right, is still remaining, that means that 375, right, 375 grams, right, must be changed over, right, into N14, right? That's going to be 75%. Sorry for that interruption. Right, that's half-life number 2. Now, our main goal is to get to 30, the question was about 31.25 grams. We're not there yet. Half-life 3, which would be another 5,700 years, would be 17,100 years. Right, if you're not too good with this, you can certainly use your calculator. All right, and that's undo that. Okay, that's going to be 17.1 times 10 to the third. All right, now we want to go, we have now 125. So you do 125 divided that by 2, you're going to take half of that amount, right, which will give you 62.5. Half of 25% is 12.5. Right, trying to give you the idea of percent and mass left over. All right, now the original sample was 500 grams, so now what has decayed into the stable product would be 437.5. Oh, yeah, we don't need grams there, sorry. And that's going to be roughly 87.5%. Last one here, half-life 4. All right, so half of 62.5 would be 31.25. All right, that's what we need in this answer. That would be 6.25%. This will give us, so now you take 17,100 and you add another 5,700 years, right? On your calculator, you should be able to get 22,800 or 22.8 times 10 to the third. All right, so just to finish the rest of this, all right, if 31.25 grams is still remaining, that means you should have 468.75 grams, right? And then we had 6.25. We had 6.25 that is remaining, right, from the 100%, and that should give us a number of, I'll put this down here, of 93.75%. All right, so for this question, you want to know how much time has passed? 22,800 years would be your answer. Okay, match the number of half-lives with the amount of time that has elapsed for the disintegration of uranium-238 into lead-206. All right, now according to your reference table, all right, 4.5 times 10 to the 9 is the half-life of uranium-238. All right, so that's going to be 4,500,000,000 years. So one half-life would be the 4,500,000,000 years. Two half-lives, now you want to take the 4.5 times 10 to the 9 and just times that by 2. All right, so 4.5, or you could just do 4,500,000,000 times up by 2. Right? Same idea. You might want to just keep it numerical form. Right? That's going to be roughly 9 billion years. 3 half-lives, we're going to add another 4.5 to that number, right? Of you have 4,500,000,000. So you're going to end up being 500 million, but we're going to have a number here of 13. 9 plus 4 is 13. All right, 4 half-lives. We're going to add another 4,500,000,000. Sorry, 4,500,000,000. Right, so the 5 and 5 will give you a 0. Carry the 1. 4 plus 3 is 7. All right, so 4 half-lives. Let's see, hold on. I may have had an error here. 13.5 plus 4.5, right? That should be 18, right? That should be 18 here. I knew I saw a mistake there, right? That should be 18 billion. And if we had another 1 there, right, that should be 4.5 more above. All right, so a little error there on my part. My fault. All right, so fill in the blanks. All right, so I can only show you this. So you had a few blanks in here. Let's go over this together. Rubidium-87 is an unstable isotope of strontium-87. The half-life of rubidium-87 is 49 billion years, and this isotope is interesting because it has not gone through one half-life on Earth, since Earth is 4.6 billion years, which is 4,600,000,000. So that's how long it takes one half-life of rubidium-7 to decay. So it has not gone through one half-life, right? It has gone through less than one half-life right now. During the first half-life, 50% of the rubidium remains and 49 billion years elapsed. During the second half-life, 25% of rubidium remains, and we have 98 billion years. So 49 billion plus 49 billion, or 49 billion times up by 2 will give you 98 billion years. It's a long time. During the third half-life, half of 25 is 12.5%. And then we're going to take the 49 billion and times up by 3, and you should get 143 billion years that has elapsed. During the fourth half-life, okay, we have 6.25% remaining of rubidium-87, right, from the 12.5, and then another half-life would be 49 billion times up by 4. That will yield 192 billion years. Long time. All right, last one is the time to climb, so you can certainly work on that on the student paste. Pretty sure you can do that. All right, good luck to you on that game. If you have any questions, try to jot down the question. I'll gladly go over those questions with you. All right, guys, have a great rest of your day, and I'll see you tomorrow.